In this presentation, I'm going to talk about analysis of variance, also known as ANOVA, with TI. First, let's discuss ANOVA. It's a method used anytime we test for equality of at least 3 population means simultaneously. Just like any other testing, we need to set up HO and H1. The null hypothesis will be all population means are equal, mu1 equal to mu2 equal to mu3 all the way to mu k. The alternative hypothesis, H1, would be at least one population mean is different. ANOVA uses F distribution, and it's always a right tail test process. So since this is going to use the F distribution, how do we find degrees of freedom when working with ANOVA? The numerator degrees of freedom will be k minus 1. The denominator degrees of freedom will be n minus k, where k is the number of groups or samples, and n is the total sample size of all groups or samples. This table shows the number of defects for 3 models in an assembly line. We want to find the degrees of freedom for attempting to compare 3 population means. We have 3 groups, so k is 3, and the numerator degrees of freedom will be k minus 1, so it will be 2. The total sample size n is 15, so the denominator degrees of freedom will be n minus k, 15 minus 3, that would be 12. We want to use this last example to test the claim at 0.02 level of significance that the average number of defects is not the same for all 3 models. Setting up HO and H1. The HO will be that the population means are equal. Mu1 equal to mu2 equal to mu3. The alternative hypothesis would be that at least one of the means is different. In this case, H1 is our claim, and the ANOVA process is always right tail test. So we're going to go ahead and use TI to solve this problem. We store the data elements from each group in L1, L2, and L3. So I stored model 1 numbers in L1, model 2 numbers in L2, and model 3 numbers in L3. Now I'm going to press a stat, go to tests, then find ANOVA. So that was a stat, arrow to tests, arrow down to find ANOVA. Once I select ANOVA, I'm going to enter L1, L2, and L3, but separate them with commas. So ANOVA, we selected second 1 for L1, comma, second 2 for L2, comma, second 3 for L3. Now we're going to press enter to execute ANOVA command. The display below shows the output by the ANOVA command. We have the CTS-F of 9.65 and p-value P of 0.003. Now, in this presentation, we're only going to use the p-value method. So we have p-value P equal to 0.003. P-value is less than 0.02 significance level. Therefore, H1 would be valid, which means we have a valid claim. Therefore, we fail to reject the claim. A new example. In a biological experiment, 4 mixtures of certain chemicals are used to enhance the growth of certain type of plants over certain time. The data below shows the growth rate. We want to test the claim that there is no significant difference in the average growth of these plants for different mixtures. And we're going to use 0.01 level of significance. Setting up HO and H1. HO will be all 4 means are equal. mu1 equal to mu2 equal to mu3 equal to mu4. The claim was that there is no difference in the means, so the claim is HO. H1 would be at least one mean is different, and the ANOVA process is always right tail test. We had 4 groups, so the numerator degrees of freedom will be 3. We had total sample size 20, so the denominator degrees of freedom will be 16, 20 minus 4. And the significance level was 0.01. Now we store the data in L1, L2, L3, L4, and then we use an ANOVA command with L1, L2, L3, L4, separate them with commas, and the p-value becomes 8.03 times 10 to the negative 6, which is in scientific notation, and will be very, very small number. P-value is less than 0.01 significance level. Therefore, the null hypothesis is invalid. Null hypothesis was the claim, and we have to reject the claim. Another example. The following table shows randomly selected exam scores from 4 different colleges of the same exam in the same semester with the same type of modality. We want to test the claim that the mean of all exam scores in these colleges are the same. Again, setting up HO, H1. We have 4 colleges, so mu1 equal to mu2 equal to mu3 equal to mu4. That would be HO. We're testing the claim that these means are the same. So that would be the claim. H1 would be at least one mean is different. And again, ANOVA is always right tail test. We have 4 groups, K is 4. The numerator degrees of freedom will be 3. We had a total of 24 exam scores, so the denominator degrees of freedom will be n minus k, in this case will be 20. There was no significance level given, So the default is alpha equal to 0.05. Storing the information in L1, L2, L3, L4 using ANOVA command with L1, L2, L3, L4, we get p-value of 0.879. P-value is greater than 0.05 significance level. Therefore, the null hypothesis is valid. Null hypothesis was the claim. So in this case, we fail to reject the claim. Now, let's suppose we're given CTSF 2.678 for 5 groups and a total size of 50. We want to find the corresponding p-value. We want to select alpha from this list to support HO. We want to select alpha values from this list to reject HO. Well, first, we're going to find NDF and DDF. K is 5. The numerator degrees of freedom will be 4. N is 50. The denominator degrees of freedom will be 45. Now we have all the information we need in order to find the corresponding p-value. So remember, the ANOVA uses a right tail test with F distribution. So we draw, we label, we shade, and whatever that area is, that would be our p-value. Using the FCDF command, the lower would be 2.678, upper would be E99, numerator degrees of freedom 4, denominator degrees of 45, and our p-value is 0.044. To support HO, we need p-value to be greater than alpha. So we choose alpha to be 0.02 or 0.01 for the recommended values. To reject HO, we need p-value to be less than or equal to alpha. Therefore, we choose alpha to be 0.05 or 0.1 from the recommended values. I hope this presentation helps you understand what ANOVA is, what ANOVA does, and how to do the testing and find the recommended significance level in case if we are given a p-value or we are given the CTSF, and then we can find the p-value.